All right, so we've just finished the welcome and the poll. It's going to be a presentation that I'm going to do for 30 minutes. And I'd request anyone who has a question who could, kind of just wait till the end of my presentation. And we would have 15 minutes dedicated to, questions and answers on the presentation that I'm about to make. Thereafter, we'll have a breakout discussion where you will be divided into smaller groups of maybe three or four, or maybe three or two. And after that, we will complete the session with a sharing in the plenary. So that's a total of 90 minutes. This workshop should finish 11 p.m. India time. It should finish 9:30 a.m. Pacific time. Right. So today's session, the presentation that I'm going to make is got to do with some of the. I'm going to start with some of the building blocks of chaos theory and why this is so relevant and important to us. So it begins with by understanding zones in human and natural systems. So that's going to be the first part of today's presentation. And I'm going to share a story. It's an anecdote that I'm going to share with you. So each of you becomes very clear of the concept of zones. So I did my MBA at Boston University in the early 80s. And we were about maybe 15 or so, 15 odd international students. We hailed from geographically diverse regions from as far as Bolivia to Japan. We were scattered all over the place. And we were a motley group. The only thing that we had really in common, there were two things. One was that we were international students. And the second was that we were all wanting to pursue a business degree. I was the president of the International Students Club, and we would engage in discussions, very often. We would get together. And at the end of some of these conversations, my friends would, colleagues, classmates would come up and tell me, "Hey, Shakti, are you right wing or are you left wing? We can't really make out, your disposition." And I would laugh it off and I would say, "Hey, I'm a right-wing revolutionary." And that would further confound and confuse people. And when I say, so then I would get the retort and say, "Oh, so that means you're a fence sitter." And I would say, "No, I'm not a fence sitter." So this ambiguity about my political leanings has been something which has been deliberate. And there's a whole personal side to it. So I came from a family which had really, I come from a family which had very diverse, in fact, opposite influences in my life at the time in my formative years. So on my paternal grandfather's side, my paternal grandfather was, awarded the title of the Rai Bahadur by the British and for his loyalty to the crown. And so those were my antecedents from my dad's side of the family. And from my mother's side of the family, my maternal grandfather was a revolutionary. He participated in what is unarguably the most outrageous incident in British India, which was the Jallianwala Bagh tragedy. And he escaped from Jallianwala Bagh, which is in Amritsar in northern India, with a bullet wound in his leg. He just about managed to save his life. So I grew up with influences that were both capitalistic, they were both socialistic, all of that. And it would become, quite awkward, very hard to remain as one composite being. So there was also a process of discovery that was going on at that point of time. And I was a voracious reader. So I would, look at, observe the profiles of people who, who claimed to be right wing, affiliated with the right wing, and also the profiles of people who were, claimed to be left wing. And not that I was stalking anyone. I was just a voracious reader. I would read the Time magazine cover to cover, in that time period. And I read that for decades. I would just keep a track of, people on both sides. And then I came across, you had a lot of people who were on the right in the US, for example, who were, you know, would have actions or affairs that would have led to abortions. So privately, there would be a lot of Republicans who would have, sort of engaged in abortions. But there were also Republicans who, or right-wing people who were very deeply committed to social causes, to charitable causes. And then I came across people on the left wing who were, champions of, injustice, champions of people who were oppressed. But they were sitting on a pile of wealth, accumulated wealth, whose antecedents were ill-gotten. So you had paradoxes, or you had, variations on both sides. And that's when I discovered that, right wing and left wing is not a compartment. These are zones, and these are overlapping zones. You'll find that even today here in India, the right wing government is committed to a lot of social causes, right? So, and then there are occasions when you have, two right wing governments in two different countries who don't get along with each other. It's not always the case. Sometimes they're inimical to each other. So this just leads us to the fact that look, these what we call as right wing or left of center, right of center, these are zones. These are not watertight. They're not fences, right? And if you were to look at the extreme right and the extreme left and place them on a circle, right, you would observe that the extreme right and the extreme left occupy an adjacent space. Do you know that Hitler was responsible for the death of 6 million Jews? And Stalin was responsible for the death directly for 3.1 million people. So when you look at the extreme right or the extreme left, there is really nothing, nothing much to draw out from that. So for me, the center was a very safe space. It was where my security lay. But then I discovered this was a zone. So I wanted to just give you that example of, what a zone is. I'm going to give you another example, which is in a natural system. So the American poet Robert Frost wrote a poem which is called The Nor'easter, meaning northeaster. And he writes in that poem that he writes that, in the US, peaches grow in Virginia. But this poet would reside in New England, which is about 800 miles further north, but he would plant peach saplings. Because there was a slight chance, a feeble chance that a peach sapling might actually grow in that region. But if you were to go further north and move all the way to Greenland, there's not a chance in hell, at least so long as climate change doesn't go that far, that you're going to be able to grow a peach tree in Greenland, and you're not also going to be able to grow a peach tree in the Caribbean. So there is no line, there's no fixed line which says that look, south of this you can't grow a peach tree, and north of this or south of this you can grow a peach tree, and north of this you can't grow a peach tree. These are zones. And if you look at the illustration, the image that I have for you, you'll find that the when one zone meets another, it's quite blurred. There's no line, there's no concrete line, there's no definite line where you step from one zone into another. And zones tend to overlap. So this is what Robert Frost wrote in his poem. Though there are no fixed lines between wrong and right, there are roughly zones whose laws must be obeyed. Now, if you've understood zones, then half the work is done in understanding chaos theory. So I'm going to move to the next section of my presentation, which is linear versus nonlinear thinking. And some of you are familiar with chaos theory and somewhat familiar, so which means many of you are familiar with linear thinking and nonlinear thinking. But I'm trying to establish linear thinking and nonlinear thinking in the context of linear systems and nonlinear systems. So a good example of a linear system would be a telecommunication system. It could be a road signaling system, which we use for traffic. A good example of a nonlinear system could be COVID-19. It could be climate change. So these are examples. But what is it that distinguishes linear thinking from non-linear thinking? When we speak of systems, and especially when you're looking at the physical sciences, the language that unites physical sciences is the language of mathematics. So the way the history of science has evolved, it has been customary to express a system in the form of an equation, a linear equation or a nonlinear equation. So what are these equations? And let's just go there. I'm trying to get to something which is fairly rudimentary. I want us to revisit this because if this becomes clear, then the rest of this whole presentation just falls in place. Right. So an equation is something which is, x is equal to 3y, or, so there is on one side, on the left-hand side, there is a dependent variable. And on the other side, there's an independent variable. But if I was to speak the language of not of mathematics, I would say that on the left side is the effect of the cause which exists on the right side. So we're trying to establish a causal relationship between y and x, between an independent variable and a dependent variable. Now, in linear thinking, there are three things that help us distinguish between a linear equation and a nonlinear equation. So the first is in a linear equation and correspondingly linear thinking, there is just one dependent variable. There is one effect that we are trying to understand. Yeah, that effect could be anything. And I have an example for you on the next slide. Now, it's also possible that in a linear equation, you could have one effect, but multiple independent variables. But every independent variable has its own direct relationship with the dependent variable, right? So when I move over to the other side with nonlinear thinking, uh, there are two things here. In nonlinear thinking, in nonlinear equations, there could be more than one dependent variable. There could be many effects, and there could be multiple causes. And the causes themselves could be related with each other. They become interdependent. So it becomes the level of complexity becomes, fairly severe. It becomes very, very, very strong. Yeah. So till the eighth grade in high school, it was, I looked at high school maths till the eighth grade was fairly simple. But then once we were introduced to quadratic equations, I used to always ponder how can a problem have, two solutions, and those solutions could be just opposite. But a quadratic equation is an example of a nonlinear equation. So I'm going to explain this qualitatively with a map, so it becomes easier for you to comprehend. Yeah, I also want to just go back to this slide, and there's one other thing that when we look at linear thinking and nonlinear thinking, in linear thinking, the change that any change in a cause leads to a proportionate change in the effect. So if the cause is changed by a certain factor, the effect is also changed by a certain factor. Whereas in nonlinear thinking, in nonlinear equations, in nonlinear systems, that is not the case. A slight change in a cause can lead to a grossly disproportionate change in effect. Yeah, so that is the other part that you've got to understand about linear versus nonlinear. But let's just take this with an example. So we had wildlife trade. There's a lot of wildlife trade that's going on, has been going on. And the wildlife trade was responsible for genetic mutation, which led to viruses jumping from pangolin to bats. And that led to COVID-19, the virus jumping to human beings. That was the antecedent of, COVID-19. And a researcher who is involved with developing the COVID-19 vaccine is not interested in looking at anything beyond this. The researcher is primarily interested in how that virus jumped from an animal to a human being. All right. And you go through it, you analyze using analytical techniques, you get to that place where this is wildlife trade. But when you look at a nonlinear map, it's telling us something very different. We are saying that, look, a nonlinear map is bringing about what is known as a, a web of causes. There's not one single cause. There are multiple causes, and these causes are also related. They're not independent. And if you see the way these arrows are structured, you have economic growth, you have corporate growth, you have population growth. So the limits of our planet are being tested today. We have corporate growth that is relentless and mindless in its pursuit of quarterly profits. There's a greater offtake of fossil fuels. There's water scarcity. There's soil erosion. All of these are leading to global warming and climate change, which in turn is leading to species extinction, which is consequently upping the wildlife trade. And this is leading to the genetic mutation that was responsible for COVID-19. So when you look at these two maps, you'll see how what a study in contrast these are. So I'm coming to the next slide, which is now when we get to science, right? And we look at, and we've been speaking about linear thinking, we've been speaking about equations, we've been speaking about systems, but I want to get to what is the science that is behind what it is to help us understand with an analogy, a simple analogy, so that everybody gets it straight, gets it right, that this is the difference between linear science and nonlinear science. And I'm going to explain this with an analogy of a game of billiards. Is there anybody here who does not has never played a game of billiards, who doesn't has never seen a billiard table or a pool table or a snooker table? I doubt it. I think everyone on this call today would have seen what a billiard table looks like. So in a billiard table, the striker is trying to strike the black ball with the help of the white ball. Now, linear science, as by way of an analogy, is the science that enables us to to map and to map out fully the direction and velocity of the black ball for every angle and every force, the level of force that is used in striking the white ball. It's a relationship between the white ball and the black ball taken from different angles and using different parameters. So the parameters in this case would be angle, it could be force. Yeah, and the effect in this case is we're looking at is the velocity and the direction, the vector of that ball. Right? So that is linear science for you. But there are three fundamental issues with this. There are three fundamental blind spots with this. So linear science has helped us in many ways. The first, the industrial revolution that we had, and most of the science, the technology that we see in our daily lives has been a big gift to mankind. There is no question about that. But what is unfortunate is that the limitations of linear science have never been fully understood. Has got to do with many factors. We're not going to have the time to go into that today. Right? So, what is nonlinear science, and what are the challenges that of linear science and nonlinear science addresses? So, the first thing is when you look at nonlinear science, here the assumption is that there is one white ball striking a black ball. But in a game of snooker, there's many different balls. Yeah, it's possible that that this one ball that is being struck doesn't just collide with a black ball. That black ball can collide with four different balls, and you would never know how to, then predict the velocity and direction of that black ball. The moment we bring in reality, we realize that linear science is just too much of a simplification. That's simplification number one. It's based on a whole host of assumptions, yeah, which don't mimic, which don't resemble reality. Number two is our universe, and you may have heard this before, our universe is known to be expanding. It's constantly expanding. It's amorphous. Our universe is not rectangular in shape. So here in linear science uses an artificial frame to do its work. Everything that Newton did and Rene Descartes did was based on an artificial frame of reality. That is not reality. It's within the limits, within the boundaries of something which is artificial that linear science was developed. So nonlinear science then tries to go beyond that and says, no, let's just mimic the real world, mimic the universe. Why should we because what happens if this white ball is struck with such great force. Sorry, the white ball strikes the black ball with such great force that it falls off the table and it goes jumping around wildly and chaotically. Linear science never ever predicted, never ever forecasted that. They just rounded it off, saying that that's not a possibility. Right, but there are times, and I have played billiards before. I in my youth, I have played billiards and I played snooker, and I've come across instances when the ball has just jumped off the table and it's gone, yo-yoing around. It's just gone on jumping all over the place. So that's the second limitation. The third limitation about linear science is that it does not factor into account the intentions of the striker. The human intentions are completely missing from linear science. Yeah, so I wanted to give you, all just the bedrock of, what chaos theory is about, and I hope this is clear. Actually, let me just pause here right now. I'm going to just pause here because in case there are any questions or any doubts, then I'm happy to kind of address those right now. So, does anyone have a question? Is it all very clear? But please, if you have a question, can you voice it? Can you just unmute yourself and speak up? Is it anybody
C-
have a question?
I, I hate to ask you to do this, but would you mind going back really quickly to the slide of the linear thinking? Yeah, right there with then no back where you had then the animals,
This one?
everything. Um,
Is
and
it this
now
one?
with all of that, with the yes,
Yeah.
that okay, wonderful. Thank you. I just wanted to be able to look at that more
Yeah.
closely, but I got
Is
it
there
now.
is there a question that you have on this?
No, I just didn't have my glasses on at the time when you put it up, and so now I wanted to be able to read for the nonlinear map because in my ecosystem restoration work, I think this is really interesting to really comprehend all of the different nuances and people tend to think more in the linear map, but no, this is how nature works with the nonlinear and everything is so connected. So this is very interesting. Thank you. I just wanted
All right.
to have another moment. So thank you.
Sure. Sure. Anybody else has a question? Comments can be kept for later, but anybody has a question where something is not understood, I want to make sure that before I proceed, that people understand what zones are. And zones are not compartments, they are overlapping. One zone meets another, it can be blurred. Uh, and the second thing I want to make sure is that everyone understands the difference between linear thinking and nonlinear thinking. Right. So I take it that there are no questions that people have understood, but we're going to have time, a few minutes at the end of this presentation. So we can revisit any question that you might have later. So when we come to chaos theory, the whole evolution of systems, sciences had to do with, I may not going to get into this, will be, but I just want you to be aware that it's 100 years ago, a century ago, we started with an Austrian biologist came up with what was the general systems theory. It was followed by something which is called cybernetics, and then there was something called complexity sciences, complexity theory. We're not going to get into a lot of academic stuff today. All I want to just, the reason I brought this slide up is that our focus today is going to be on complexity theory. But when I get into complexity theory, there itself, there are a lot of pillars. You have chaos theory, you have fractals, you have dissipative structures, we have complex adaptive systems. So for our session today, this our focus is going to be on major focus is going to be on chaos theory, and our minor focus is going to be on fractals. Yeah, what are fractals and what is chaos theory is what I'm coming up with next. Right. So there is this person, Edward Norton Lawrence, who is considered as the father of modern day meteorology, the late Edward Lawrence. And in the 60s and the 70s, he came up with, techniques to try or his whole purpose, his mission was to try and forecast weather, to be able to predict weather. And he came up with started experimenting and came up with three nonlinear equations, which, as I explained to you, are quite different from, linear equations. Nonlinear equations means this complexity. If you were to look at the weather today, there is like God knows how many factors that would, be responsible for weather. But he was looking then at three equations, and that had to do with, convection, vertical temperature, horizontal temperature. We're not going to get into that. But what he did was he ran these equations. He had these runs, and we had high-speed computing in the 70s, mainframes, and a lot of other stuff that the whole evolution of computing that happened in the 70s made it easier for people like Edward Lorenz to run these nonlinear equations. And what he found was that each of these equations resulted in a beehive of outcomes. There were like really a very large number of outcomes that each one of these equations generated. What he observed was that there was a lot of emphasis that had to be given to initial conditions. Initial conditions are your starting point. If there was a slight change in one of the factors that was going to influence weather, yeah, it could lead to drastic changes in that weather forecast. Yeah, a very slight mild change in convection rate or a rise in temperature, any one factor, humidity, whatever. Yeah, it could lead to dramatic changes in or disproportionate changes in the weather forecast. So what he discovered was that essentially weather functions in terms of zones. These are called zones of rules. The technical language for this is called attractors. So the weather system essentially is governed by a different set of attractors. Now, let's take this with an example. If you look at the weather in England, it is notoriously fickle. It is, if you look at England or Ireland, the weather is just so unpredictable. But still, despite the fact that it is so unpredictable, there are certain things which are very predictable about English weather or Irish or weather in Ireland. And that is that it moves within a zone. And what that means is that England will not ever experience a monsoon, will not experience a drought. It will not experience a hurricane. So there is predictability even when at the face of it, what is apparent, what we living in England, if you were in London today, if any one of you is in Great Britain today, you would think that the weather is so unpredictable. But if you look at the entire picture, there is the variation between two ends of that zone. The lack of prediction is just within that zone, but the zone itself is very predictable. There's no hurricanes. There's there's no drought. So things like these. So this was the discovery that he made of zones and zones of rules, which are called attractors in chaos theory. This was and what he also discovered was something which is called these are attractors. This is called the Lorentz attractor. And these attractors, now what you see is that every equation has a certain trajectory. The colored dots that you are seeing here on this in this visual are nothing but possible sets of values for each of these nonlinear equations that he ran. And he ran them again and again and again. Yes, so I'm going to just step back for a minute and give you another example. Yeah, it's a more rudimentary example, and I explain this to you with a rudimentary example. Yeah, so I'm a blog writer. Okay, I write for fun, and I write seldomly, but I manage to write like about 7 to 10 blogs a year. And in 2025, I have penned four blogs in February. I penned one blog in April, one in June, and one in September. And I'm hoping to do one or two more in this holiday season. So if I do two more, that would be 9 blogs that I would have clocked this year. Does anyone see, is there any pattern in my writing? Does anyone think or feel that there is a pattern? Is there any pattern? Can somebody please speak up in what I just told you? Is there any pattern?
Yeah, it is spiraling and it's
How is it spiraling? I'm starting from 4 blogs in February.
no. I'm just seeing the image in front of me as
No,
you say.
don't look at the image. I'm talking about my
Okay.
blog. I want to
Okay.
explain this image with a rudimentary example. Do you see any pattern in my having written 4 blogs in February, one in April, one in June, one in September, and hopefully maybe one or two in December? Is there any
Yeah.
pattern that you can make out?
Maybe more in the winter months in the northern hemisphere and less in the summer months.
Okay,
That's the only pattern.
that's interesting. But supposing I was to remove the months,
Okay.
and I was to tell you you could start at any point of time, yeah,
No,
and
I
you
don't see a pattern.
don't see a pattern, correct?
I think it's random.
It's random, right? So, but if I showed you the history of my blog writing over the last 7 or 8 years, you'd find this pattern, which I just took you as what you said is no pattern. You'd find it repeating itself. And
Maybe the earlier part of the year, Shakti, you are more excited and energized. You have a lot to share, and therefore four blogs come at a
No,
random time.
he said remove the months and
Achha,
but
but still, it's like the
okay,
starting.
okay, you bring the months back, all right? So if
so
you,
Shakti, I
go ahead.
think the difference comes that when you mention the months and we ask the question, is there a pattern? Our mind is looking at the time frame of 12
True,
months
true,
and
true.
seeing a pattern within that. But moment you say 7 years, then the time frame changes and there's repeatability within the of each 12 months across the years. And
True,
then
true.
the pattern might come in.
True, very true. You hit the nail on the head. And I want to give you credit for having looked at the winter month, a bit of it.
Hmm.
So, the reason is not so much of winter, but it's the holiday season. It's the time when
Yeah.
everyone is chilling. I'm chilled out, and my audience, everyone is chilled out. So that gives me an incentive to write more in the time period of December, Jan, and Feb. So if you look at the pattern, if I actually studied my own pattern of for the purposes of this presentation, and I observed that there is a concentration of blog writing in the months of December, Jan, and Feb. Yes,
Yeah.
so now that is a pattern which, when I expand the basin of time, when I look at a particular series of events or values in a narrow basin of time, I'm not able to detect any pattern. But if I was to expand that basin of time and from 1 year to 7 years, then that pattern becomes very evident. Right. So in this case, what Edward Lorenz did was he ran these simulations again and again and again and again. And this is just a simplification. So you have the trajectory of each of these, each of these, each of these runs. And what is also very interesting is that no trajectory ever repeats itself. As
Hmm.
I'm trying to draw a distinction between identical
Hmm.
and similar. Yeah, these are not one of these trajectories is identical, but they are similar. All of these are similar. They have a similar pattern. And what Edward Lorenz discovered was that if the factors, if the system of weather was disturbed to such an extent that it was sufficiently disturbed, right? It could lead to a major, massive, drastic change in a weather pattern. Yeah, so that was his real claim to fame. That was a finding, and it just completely revolutionized not only weather forecasting, but I mean the whole science of nonlinear science. It gave a real impetus to nonlinear science. Yeah, so at the end of it, what you're seeing from this image is that look, and you go back to the example that I gave you of the billiard pool table, the universe is neither random nor uh, nor structure. It is both. It is neither random nor mechanical. It has got elements of both. There is randomness and limits that exist in our universe, and therefore, for order and disorder are essentially embedded in each other. So this was the big discovery that chaos theory meant that look, when there is chaos, there is also order. Some of you may be familiar with the Chinese yin and yang.
Yeah.
Yin is embedded in yang, and yang is embedded in yin. So if you look at any hurricane today, a hurricane eventually will dissipate. It will disappear and it will be restored to calm. So the seeds of calmness already exist in a hurricane for it to find its way out and for it to return to normalcy. So in natural systems, what Edward Lorenz, the significance of his discovery was that there is order in disorder, there is disorder in order. So these are not, in a manner of speaking, antithetical, they coexist. And that is the fundamental truth about our lives and the fundamental truth about the universe. This is just another visual of the Lorentz attractor. These are also called strange attractors because they deliver a strange shape. They come up with, and there are many different types of strange attractors, but we're not going to get very technical here today. I want to cover one or two more points here. There is something which is called the butterfly effect. So when Lorentz was doing his work, he also postulated, you know, he came up with this postulation called the butterfly effect. So the butterfly effect simply means that changes that could be as minute as the flap of a butterfly's wings could lead to a tornado. So a butterfly that was flapping its wings in Brazil could lead to a tornado in the Caribbean or in some other geography. Now that was a postulation, and as a scientific principle, it is true. It is, but I want you to know that this is a metaphor. It is not literally the case that look, the the flap of the wings of a butterfly will lead to or tornado or hurricane in some part of the world. But the principle behind this is scientifically true. That is the postulation that he came up with, which is well known today as the butterfly effect. Now, some of you, I'm going to spend a minute or two on fractals because this is something which is very associated with chaos theory. It's a cousin of chaos theory, and they go kind of hand in hands. So when we speak of fractals, think of a cauliflower, think of a broccoli. Yeah, if you break a broccoli, a stem of broccoli, and you make it smaller and smaller, you'll find that the pattern is repeating itself in a cauliflower or a broccoli. Yeah, this is an example of fractals. A fern is an example of a fractal. So fractals means patterns that constantly repeat themselves. Yeah, so the uh, the Lorentz attractor, all strange attractors have the characteristics of a fractal. So if you saw this earlier graph, there is self-similarity, right? Would you agree that these shapes that are formed are similar? They're not identical, but they are similar. The
Yeah.
whole concept of similarity exists in fractals. It also exists in strange attractors. Right. So now what was this whole thing? How did fractal geometry or how did fractal thinking come about? So uh, Benoit Mendelbrot was a researcher at IBM. By the way, I spent 15 years at IBM. I retired from IBM. But we didn't have an overlap. Mendelbrot was there active in the 70s and the 80s. I don't precisely know when he retired from IBM, but he was a researcher. And what he identified, and he was toying around with, when somebody asked him to measure the coast of Britain, it just struck him, how does one measure the coast of Britain? Now, if he or any one of us is to take 100-mile ruler and we insist that, two ends of the ruler are to touch the coast, we would in the process miss out on a lot of the coastline. The recorded value of the coast would be much lower than what it would be in reality. Am I correct? Am I fair in saying that?
Yeah, sure.
Yes. But if instead of having a 100-mile ruler, I had a 1-mile ruler, sorry, a 1 foot ruler, and I started did the laborious job of measuring the coast, I would come up with a more accurate estimate of the British coastline. Would that be, again,
Yeah.
fair?
Yeah.
Right. So this was the whole theory of fractals, that when you look at a coast, when you measure it when you look at it under a microscope and you look at it very minutely, the patterns that you find in a coast and for that matter, any coast repeat themselves. And then there are things like jaggedness and all, but we're not going to get into that. But I just want you to know that, this is the concept of fractals. And here's another example of fractals. If you were to look at the cloud formations, and if you were to look at the edge of the clouds and magnify them 10 million times, yes, 10 million times, you will find that these patterns are just repeating themselves, which may not be obvious from when you see this picture, but when you get to it very minutely, up and close, you will find that these are patterns that repeat themselves. So that was this whole idea of fractals, which brings me to
Sorry, does that connect with the Fibonacci sequence?
Uh, I'm not sure about that.
Okay,
I'm not. I'm sorry. I don't have the answer for that. But if
okay,
there's
fair
anybody
enough.
else, if there's anyone else in the audience who see, I know Fibonacci sequence from that movie.
Yeah,
Which is the movie by Dan Brown's movie.
Dan Brown. Yeah,
Yeah.
no, so it's a mathematical
Angels
construct
and
which is
demons.
found to be in a lot of things in nature.
So
Yeah.
maybe it is. Yeah. It's just that I'm not aware of it. But
Okay, fair
is there
enough.
anybody else on the call who is aware can answer that question?
I mean, I know what a Fibonacci series is. It's there in Dan Brown has brought, I think it's Angels and Demons, where he talks about that.
Is there in the one which has the Da Vinci Code?
Yeah,
No,
could
so
be.
I was really referring to whether that is the reason behind the similar patterns that you are talking about in cauliflower and clouds and so on.
Yeah, absolutely. There's also golden ratio based on the
Yeah.
Fibonacci series.
Right. Okay, carry on.
All right, but thank you for bringing this up. Yeah.
Mhm.
So
No, in
that's
fact, the seashells that we have, they're also arranged in the pattern of the
Yeah,
Fibonacci series.
yeah.
And if a woman has very good hair, till here, and she does it like this, that's also a very Fibonacci series pattern from the head to the back.
oh
So,
wow, that's interesting, Akash. I can see that you've been observing a lot of women around.
no, I've just been observing Fibonacci series,
All
being
right.
very
Okay,
fond of it.
great. All right. So, some of you familiar with this idiom, the last straw, the straw that broke the camel's back? It's in popular folklore, right? Has anyone who's not come across this idiom, the last straw, the straw that broke the camel's back?
It's a common saying.
Yeah, it's a common saying. So I'll relate it to chaos theory and then come back to this. So it's the last straw is the straw. Okay, let's explain it with a more rudimentary example. So there is this guy who has had 8 highballs, can hold his drinks, is speaking absolutely fine. He's in his senses, and his diction is clear. He's not blurred. And then the ninth drink is when he has the ninth drink, something goes awfully wrong with this guy. His diction becomes blurred and he starts blurring, and he can't, and he's going all over the place, and he's people will say he's lost it, right? So he's moved from one zone to another zone. It's that one single drink that has got him to move from one zone to another zone. We all human, as human beings, we're governed by zones. We may not think in terms of zones, but they're there, right? So the last straw is nothing but the straw that gets the camel to move from one zone to another zone, and the rules change. And the rules change so dramatically that it ends up breaking the camel's back, right? So this is an example of the straw that breaks the camel's back. Other examples of this could be the weather. If you look at the Earth's system today, and you look at the hottest region and the coldest region on Earth, it's probably between 50 Celsius and minus 50 Celsius. What is it that makes the Earth, remain in this zone? There is a wide zone. What is predictable every day of our lives, hopefully, so long as climate change doesn't push us into another zone, is that we can predict that our temperature on planet Earth is going to remain within this zone. But we know when we look at the record of the ice ages, we look at all of this, that is not necessarily the case. But at least in our lifetimes, we are seeing that this is
Options. Option one,
Okay. So that was the example of weather on Earth. I'll look at our body temperature. It is between 36.1 Celsius and 37.2 Celsius, which is 97 Fahrenheit to 99 Fahrenheit. It's our normal body temperature. And it can fluctuate in that we have our own cooling and heating mechanisms built into our body that regulates our body temperature. But the moment we cross 99 Fahrenheit or 37.2 Celsius, we're entering another zone. And that is governed by different rules. It's governed by different behavior in terms of what the patient actually experiences, right? So what is it that would then just push us into another zone? So that really is the significance. And you can take this into social sciences. You can take this into a dictatorial government that is authoritarian in nature, and when the leader dies, or where if you have a lot of stress coming in from the outside, at some point of time, that system will completely collapse, right? So what is that one event? What is that one event that could trigger, let's say, the Arab Spring? What was it? What is it that pushed the Arab Spring from one zone into another zone, right? This is zones. This is what chaos theory is telling us. That what we may just think as taking things for granted, but it could be something very minor that could lead to a drastic set of consequences. And these consequences could be for the positive, for the better, or for the worse. Yeah, also another example would be of organizations. Okay, sorry, before that, another organization could be of democracy. If you have democracy, a thriving democracy is a democracy where you have the rule of law, but you also have sufficient room for political dissent, for discussion and elections. When these two are really in harmony, then things really work beautifully. It's a vibrant democracy. And an example closer to our daily lives, for those of you who work in organizations, if you're working with any organization, and I've worked with different types of organizations. I've worked with organizations that are very tall, very rigid in their structures, and I've worked with organizations that have been extremely flat. So it all depends on, can organizations instill a balance of policies where some things are simply not compromisable, but but a lot of freedom is also given. A good example of this would be the company Spotify, yeah, which unleashes creativity of its employees, but also within a certain set of bounds, where certain set of policies which are absolutely uncompromisable. So that is the significance of the last straw, the straw that helps you move from one edge of a zone to another edge of another zone. Yeah. So this then comes to a term which some of you may have heard of. It's called the edge of chaos. And the edge of chaos is a narrow transition zone. And this is a quote from Mike Jackson, who's a professor of systems thinking in the UK. The edge of chaos is a narrow transition zone between order and chaos that is extremely conducive to the emergence of novel patterns of behavior, and a system driven to the edge of chaos is likely to exhibit spontaneous process of self-organization. I'll give this to you with an example. Yes, so if you look at democracy in Switzerland, it's a really fabulous example of how democracy is thriving in Switzerland. I can't think of a better example. Of course, there will be other examples also, and then the examples of failed democracy also. But essentially, edge of chaos means that can our lives can our lives be sufficiently flexible and also sufficiently constant? Can we have a union of both of these? And when we have that union, it is known as living at the edge of chaos. All right, so I'm going to just come to the last section and then open it up for questions. So there is this debate about free will versus determinism, and I'm just quickly going to take you through. I'm also doing a time check. I think I'm overshooting, but I'm going to try and wrap this up quickly. So Free will is defined as the power of acting without the constraint of necessity or fate, the ability to act at one's own discretion. Volition is the faculty or power of using one's will. Determinism is the doctrine that all events, including human action, are ultimately determined by causes regarded as external to the will. And fate is the development of events outside a person's control regarded as predetermined. These are all from the Oxford Dictionary. This is just the dictionary meaning of free will and determinism. I'm going to give you a quote from a book written by Dr. Paul Fleischman, and this is from an essay. It's the final essay in the book, which is jointly authored by he and his son Forrest Fleischman. And I'm just going to leave you pondering about this, but there's some really very hard-hitting messages that come across in this book that I picked up. Causality operates now. The environment conditions us, and we make choices that express us. But genetics is mere fate. In this viewpoint, causes that lie outside our own volition make us who we are. We are stuck with a hand that has been dealt by some other force. We are understood as subject to luck. Although we have some power to change, and although our current life follows the laws of cause and effect, our birth does not follow those laws. It is an irony that this worldview, which is often mislabeled as scientific, is based on serial suspension of causality. The effects of our actions are believed to commence at birth and cease at death. Before and after, personality submerges into a fatalistic, acausal universe. I want you to, you were going to get a copy of this deck, and I want you to go this, again. Uh, and just chew on that. And it may take you time before you get it. But I'm going to give you another quote, which is hopefully will make, Dr. Fleischman's that passage a little more easier to understand. And this is from Peter Senge, who is a systems thinker at professor at MIT. And he sums it up beautifully in one sentence. Systems thinking is the ability to understand the consequences of my own actions. If there are consequences of my own actions, then I have a choice. I have a choice of the kind of food that I eat, the quantity of food that I eat. I have a choice of being corrupt or honest. I have a choice of insulting somebody or not insulting, or being kind to someone. I am essentially governed by choice, but I'm also governed by the consequences of my own actions. And when I look at consequences of my own actions and that billiard pool table, which I introduced to you earlier, and imagine that instead of having two balls, you have hundreds of balls that are whizzing past you. The consequences of my actions depend not only on the angle and force with which I strike that ball, but also the uh, the the velocity and the direction of all the other balls that may collide with that ball. Yeah, so we are interdependent. So this is just to let you know that look, fate and determinism, sorry, excuse me, that free will and determinism are like yin and yang. They're embedded in each other. It is not a question of either or. Right? I just want to leave that thought with you. You're going to get a copy of this presentation. You're going to get a copy of the transcript as well as a recording of this session. So before we jump into the breakout session, I have room for one or two questions, and then we get into the breakout discussion. Anybody has a question or questions on what you have gone through so far?
I have one.
Yes, please.
When you mentioned about the last straw that pushes a system from zone 1 to zone 2,
Yes.
isn't it per force that you recognize that last straw only as a post facto? Because there is no way of knowing which straw would end up being the last straw.
That's a fabulous question. Yeah. So thank you. Thank you for
Yeah,
that.
it is.
Yeah. So I'll explain this. See, nonlinear science doesn't give us the the means to predict everything precisely.
Hmm.
But it endows us with a lot of foresight. And I want you to understand the difference between foresight, forecast, and prediction. A prediction is something which you can do in a linear system fairly easily.
So,
Everything's defined, everything's known, right? A forecast is a best guess estimate of what the weather is going to be in the next 6 hours or in the next 2 or 3 days. Foresight is something which is more directional rather than precise. It's not going to be able to pinpoint, not necessarily going to be able to pinpoint, oh, that this is, can you identify the last straw? The guy who gets drunk on the ninth drink may, after an experience post facto, as you rightly pointed out, realize that his limit is at 8 drinks and no more.
yeah.
Right? But it's post facto. But if you have foresight, then you may not want to go as far as 8 drinks. You may want to be content with three.
Yeah, but then the foresight is coming from a series of such events in the past, each of which you recognize the tipping point post facto. And from there, you zoom out and see a pattern saying, okay, it's 7 to 9 drinks is when I go over.
Yes, yes. So you're right in saying that.
It's
You're
not really foresight in some intuitive or a prescient kind of way. It is it is modeling of your past 10 times you created a scene at a party because you drank too much.
Okay, so let's just take and yes and no. I would agree and also not agree with you. And I'm going to give this Rajneesh with an example which is there in the breakout session.
Okay,
And I'm going to come to address this, but can I move to the breakout session? Is there any
please.
compelling question that anyone
Please,
has? Yes,
one
yes.
more thing, Shakti, to answer Mr. Rotagi's question, I mean, just to supplement, if we have huge computing power, take for instance like quantum computing to be able to calculate those that what straw would be a last straw, aren't we getting very close to the point that we can identify the tipping point? It's all about mathematical precision, right? At the end of the day.
Yeah, so that's the linear thinking way of approaching it, excepting on a very large number of examples or data
Yeah.
points.
Yes.
But it's still the same principle.
See, the
Right.
last straw is from folklore. Okay, it is not from system science. It is. I brought this in to bring in the folklore element. It's an idiom.
Hmm.
All right,
Yeah.
but Rajneesh, to give you the example why there will be foresight, because when you start thinking in chaos theory, look at a relationship like marriage. Uh, it, I'm not talking about you or me, but in the case of a couple, if you're thinking non-linearly, if you're looking at things from a relationship from zones, then you should be able to have the foresight as to, hey, at what stage might my marriage rock? And there's no
Hmm.
past experience here. There's
Hmm.
nothing post facto.
But
Yep.
Shakti, that's a qualitative analysis and not a quantitative analysis to
But
understand that.
true. So chaos theory is actually pushing the whole narrative from quantity to quality. See, there's a chaos theory. We can spend a lot of time on it, but we'd miss our timeline for
Yeah.
today.
Yeah.
There's some things which are called the phase portrait in chaos theory, and that when that phase portrait kind of changes, the whole system can be in a state of disarray. So chaos theory is really pushing you in the direction of it's qualitative insights rather than quantitative insights, which
Yeah.
is why this element of foresight is still very true. I don't need to get to level eight drinks to get to know my tipping point or get to know what the last straw is.
Yeah.
Let's look at the questions that I have. We're going to get into breakout groups. I want to see how many people there are right now. I think there's how many? Is there 24, 23? Can somebody tell me how many people are there on this?
So 19 right
20.
now. Yeah.
19. Okay,
Or
so
19.
we're gonna do this in groups of three, and one group maybe in four. But I'm also going to put this in the chat, and I want you to get into a group discussion and choose. Each one of you has 5 minutes and chooses one of these topics. All right. Are human relations governed by zones? Could the incidence of divorce or any other separation be seen as an outcome of moving from one zone to another? Second, do you think that the Ukraine-Russia war was precipitated by a single outrageous act, or was it on account of relations between governments moving from one zone to another? How structured is the organization you work for? Is it positioned at the edge of chaos, or is it overly structured or overly flexible? Is there a metaphorical example of the straw that broke the camel's back in your personal, professional, or social life? Have you ever experienced in one moment of insight multiple doors and opportunities opening up in front of you towards which you had been spending an endless amount of time before? Right? These are the questions. I'm going to put these in the chat for you to.
I'll take the Ukraine war one.
Yeah.
All of them are very interesting questions, I must say. You thought them yourself?
Yeah, I've taught them myself.